Welcome to another deep dive. You know, you all really wanted us to get into this one, the physics of impossible technologies. So we're going to use Michio Kaku's book.
Physics of the impossible.
Exactly. That's our guide for today. And it's really cool how he goes through, kind of breaks down, what might actually be possible someday.
Yeah.
Versus like what's going to stay, firmly in the realm of science fiction.
It's so cool how he categorizes them all into these different classes of impossibility, too.
Yeah, right.
Some are much closer than others, and some, maybe we could see in our lifetimes.
Okay, so let's unpack this a little bit.
Yeah.
And I think a good place to start is with something that everybody's familiar with, at least from science fiction. Force fields, in deflecting, energy blasts and levitating objects.
Yeah.
I mean, who hasn't dreamt of that?
Right.
But is there any real science behind it?
Yeah, there is, actually. Really? Yeah. We can trace the concept all the way back to Michael Faraday.
Oh, wow.
And his discovery of electromagnetic fields. And he showed that, fields can exert force across empty space, like when a magnet attracts metal.
Okay.
So that's the core principle behind force fields.
Okay, so we're not just talking about, pure fantasy here.
No, not at all.
Okay.
Scientists are exploring some pretty wild ideas.
Plasma windows?
What's a plasma window?
So imagine superheated plasma contained by magnetic fields, creating a barrier strong enough to separate a vacuum.
Oh, wow.
Like space from ordinary air.
Wait, so you're saying, we could potentially have a window into space?
Yeah.
That's insane.
It's a concept that's being explored.
Yeah.
Large-scale plasma windows are obviously far from reality.
Right.
But it shows you how scientists are thinking about, manipulating fields.
Yeah.
To create those force field-like effects.
Okay, so what about levitation?
Yeah.
I mean, we've all seen hoverboards in movies.
Right.
But that's always seemed like pure movie magic.
Well, magnetic levitation already exists.
Yeah, like maglev trains, but levitating a person, that's where things get a little more tricky.
Right.
Kaku suggests that with room temperature superconductors, which could create incredibly strong magnetic fields, we might be able to use something called diamagnetism.
Hold on. Are you saying hoverboards could actually become a reality?
Well, potentially.
Oh, wow.
Diamagnetism is the property of certain materials to repel magnetic fields.
Okay.
So if we can figure out room temperature superconductors, we could create fields powerful enough to levitate diamagnetic objects, even people.
That would be revolutionary.
It would.
I mean, the superconductors that work at room temperature, that feels pretty sci-fi in itself.
True, but Kaku categorizes force fields as a classifier, impossibility, meaning it's potentially achievable within a century or so.
Oh, so you're saying maybe not for us,
yeah,
but future generations might be zipping around on hoverboards.
They might be.
Okay, so force fields, though, still far out, might not be completely impossible?
Right.
But what about other sci-fi staple, invisibility?
Who hasn't dreamt of just disappearing at will?
Absolutely.
Right.
Well, invisibility might seem magical, but it really boils down to manipulating light. And for that, we have to thank James Clerk Maxwell and his groundbreaking equations describing electromagnetism.
Okay.
That was revolutionary for our understanding of light. And it lays the foundation for even thinking about invisibility.
Okay, so how do Maxwell's equations connect to making something vanish?
Well, it all comes down to the index of refraction, which describes how light bends when passing through different materials.
Okay.
Like how a straw looks bent in a glass of water?
Oh, yeah, right? Yeah, the water bends the light.
Exactly.
Making the straw look broken.
Right. So now imagine manipulating the index of refraction of material to bend light completely around an object.
Okay.
So the light wouldn't reflect or scatter off of it, essentially making it disappear.
So bending light is the key to invisibility. Is that how they do it in the movies? Well, movie special effects are one thing, but scientists are working with what are called metamaterials. These are substances with engineered optical properties that can bend light in unusual ways. They've already created metamaterials that can bend microwaves, making objects invisible to that kind of radiation.
So invisible to microwaves, not visible light.
Right.
So are we still a ways off from like a, Klingon cloaking device or something?
Look, I think visible light is much harder.
Okay.
It requires controlling billions of atoms with nanoscale precision. a technology that's still developing.
Right.
And plus, even if we could perfectly bend visible light, there might be imperfections, like a faint distortion.
Oh, okay.
Similar to heat waves shimmering above a hot road.
So you might see a slight shimmer, but otherwise the object would be basically invisible.
Pretty much.
Wow, that's pretty cool.
Yeah, and the fact that we're even exploring this possibility shows how far we've come.
Right.
Kaku also categorizes invisibility as a class, impossibility.
Okay.
So theoretically possible, though, with significant hurdles to overcome.
Well, I'm definitely adding an invisibility cloak to my wish list for the future.
Good luck with that.
But for now, let's shift gears to something a little bit more destructive.
Okay.
The Death Star laser.
Oh, yeah.
That planet-destroying weapon from Star Wars? I mean, that always captured my imagination.
Right.
Even if it is a little bit terrifying. But is there any science at all behind that concept?
Well, to even approach that concept, we need to understand nuclear fusion.
Okay.
Which is the process that powers the sun.
Right.
It releases far more energy than any chemical reaction.
So harnessing the power of the sun.
Basically.
I mean, that's a pretty ambitious goal even for a fictional supervillain.
It is, but scientists are actually working on fusion energy right now.
Really?
Yeah. ITER is a massive international project that aims to build a working fusion reactor.
Wow.
And if successful, that could revolutionize energy production.
Okay, so fusion power is a real possibility.
Yeah.
But could it be scaled up to create a planet-destroying weapon?
Oh, wow.
I mean, that's a whole other level.
It is interestingly, during the Cold War, the U.S. explored nuclear-powered X-ray lasers for missile defense.
Wow.
It was called Project Excalibur.
Yep.
And the idea was to use the energy of a hydrogen bomb to create incredibly powerful laser beams.
So they were actually trying to build something like a Death Star laser.
Kinda.
Did it work?
Well, Project Excalibur faced numerous technical challenges and was eventually abandoned.
Okay.
Scaling up that technology to destroy a planet would be astronomically difficult, requiring mind-boggling amounts of energy.
So a Death Star laser is theoretically possible, but not something we need to lose sleep over anytime soon.
Not really, no.
Okay, good. I'm glad to hear that.
Yeah.
All right, let's jump into another mind-bending idea.
Okay.
Teleportation.
Right.
Beam me up, Scotty. The classic sci-fi concept.
It is.
But is there any real-world basis for it at all?
This is where our understanding of physics gets really weird.
Go.
Teleportation is completely impossible according to Newtonian physics.
Right.
But in the quantum realm, things get a lot more interesting.
So quantum mechanics.
Yeah.
That's where things start to get really strange, right?
Strange, but incredibly powerful.
Right.
Quantum mechanics governs the behavior of matter at the atomic and subatomic levels.
Yeah.
And it allows for phenomena that would seem like magic to Newton.
Okay, I'm intrigued. How does quantum mechanics make teleportation possible?
Well, it starts with the concept of quantum leaps.
Okay.
Electrons, for example, behave like waves. They can disappear from one location and reappear in another instantaneously.
Boy, they just vanish and reappear? How is that even possible?
It's one of the mysteries of the quantum world. It's been observed and measured.
Wow.
And it's this ability of particles to exist in multiple states simultaneously that opens the door to teleportation.
Okay, so teleporting an electron is one thing, but a person?
Yeah.
That seems like a giant leap.
That's where entanglement comes in.
Okay.
It's a bizarre quantum phenomenon where two particles, even if separated by vast distances, are linked in a way that defies classical physics.
Okay.
So imagine two coins flipped at the same time, always landing on opposite sides, even if they're miles apart. That's the basic idea.
So even if they're far apart, they're still connected, like some kind of spooky action at a distance.
Exactly. Einstein himself struggled with this concept.
Right.
But experiments have confirmed it's real.
Wow.
And this entanglement is what makes quantum teleportation possible.
So how does entanglement actually allow you to teleport something?
Well, instead of physically moving the object, you transfer its quantum state to another particle, even if they're far apart. It's like sending a blueprint that lets you rebuild the original object somewhere else.
So you're not moving matter, but the information that describes it.
Right.
That's pretty wild. But has anyone actually achieved this?
Well, scientists have successfully teleported photons, atoms, and even light particles.
Really?
Yeah, it's groundbreaking, but scaling it up to larger objects, let alone a person, is a completely different challenge.
So where does teleportation fall on the impossibility scale?
Well, Teleporting large objects is firmly in class 2.
Okay.
Meaning it's impossible with our current understanding.
Yeah.
But the fact that quantum teleportation is even possible is mind-blowing.
It definitely is.
And it has potential applications in computing and communication.
Wow, this is a lot to process.
It is.
What other impossible technologies are we going to unpack?
Well, we've tackled force fields, invisibility, and teleportation.
Right.
Next, we can delve into the possibility of telepathy.
Oh.
Communicating directly with another mind without any physical contact.
Now that's a deep dive I'm really looking forward to.
I think it'll be fun.
But maybe we should give our listener a moment to digest all this incredible information.
Probably a good idea.
We'll be back soon to explore the world of telepathy and other mind-bending technology. All right, welcome back. Are you ready to dive into the world of telepathy?
I am.
This is a good one. I mean, the idea of, reading minds or communicating without words.
Yeah.
It's always fascinated me.
Right.
It's like a superpower straight out of science fiction.
It's true. It's captured our imaginations for centuries.
Right.
It often appears in mystical and supernatural contexts. But as technology evolves, the line between mind and machine is becoming increasingly blurred.
So are we getting closer to turning science fiction into reality?
Well, in some ways, yes. We already have brain-computer interfaces that allow people to control devices with their thoughts. And techniques like fMRI and EEG are being used to read minds in a limited sense.
Wait, hold on. You're saying we can actually see what someone is thinking?
Not quite see their thoughts like reading a book.
Okay.
But these techniques can detect brain activity patterns associated with certain thoughts or emotions. So if someone is shown a picture of a cat, an fMRI scan might show increased activity in the part of the brain associated with recognizing animals.
So we're not at the matrix level of mind reading yet.
Right.
But we can get some basic insights into brain activity.
Exactly. And it's important to remember that current brain scanning technologies are still limited.
Okay.
They can detect general activity, but not decipher complex thoughts or ideas.
So no plugging into the matrix anytime soon.
Not yet.
Probably for the best.
Probably.
But where does this technology go from here? I mean, where do we go from here?
Well, Kaku suggests that we might one day develop a dictionary of thought. So by correlating specific brain activity patterns with particular thoughts and emotions, we could potentially decode more complex mental processes.
So a dictionary of thought.
Yeah.
That's both incredible and a little unsettling.
Yeah, it is.
I mean, imagine the possibilities, but also the potential for abuse.
Absolutely. The ethical implications are huge.
Yeah.
Privacy violations, manipulation, even thought crimes.
Right. These are all concerns that we need to address as this technology advances.
Yeah, it seems like a Pandora's box that we might not want to open.
Yeah.
It's definitely intriguing, but it comes with a lot of baggage.
It does.
So let's shift gears to another fascinating concept, psychokinesis.
Okay.
The ability to move objects with the mind.
Right.
Is that something we could ever achieve?
Psychokinesis is a tough one.
Yeah.
Unlike telepathy, which has some basis in neuroscience and brain-computer interfaces, psychokinesis seems to violate the known laws of physics.
Yeah.
There's been a lot of research, but nothing conclusive.
So no Jedi mind tricks anytime soon?
I don't think so.
So it's basically unproven, but I'm curious, what does Michio Kaku have to say about this?
He does bring up a thought-provoking idea from Star Trek.
Okay.
Do you remember that episode where the Enterprise encounters beings with seemingly godlike powers?
Yeah.
It turns out they're not gods at all.
Right.
But ordinary beings who can mentally control a central power station that carries out their wishes. Oh, right. It's like they're manipulating technology with their minds, not directly controlling matter.
Exactly. And Kaku suggests that future technology might be able to mimic some aspects of psychokinesis.
Okay.
He points to nanotechnology as a potential avenue.
Nanotechnology. Those tiny robots that can manipulate matter at the atomic level.
Yes, imagine trillions of nanobots working together to rearrange atoms.
Wow.
In theory, they could be programmed to move objects or even assemble them from scratch.
So it's not telekinetic powers, but advanced technology that could achieve similar results.
Precisely. Nanotechnology is still in its early stages, though, and there are enormous challenges to overcome.
Yeah.
Building and controlling trillions of nanobots is no small feat.
I can imagine.
Yeah.
It seems like true psychokinesis, whether it's, through mind power or advanced technology, is still pretty far off.
It seems that way.
Yeah, but let's shift our focus to the biggest unknown of all.
Okay.
Extraterrestrial life.
The big question.
Are we alone in the universe? I mean, it's a question that has captivated humanity for centuries.
It really has, and scientists have been searching for answers for decades,
Right.
using tools like the famous Drake equation.
The Drake equation, the one with all those variables about stars and planets and the likelihood of life and all that.
Right. The problem is that many of those variables are still unknown.
Right.
We're constantly making new discoveries that refine our understanding of the universe.
Yeah.
But there's a lot we still don't know.
So is the Drake equation more of a starting point for discussion than a definitive answer?
Exactly. It's a framework for thinking about the problem. Interestingly, recent discoveries have both increased and decreased the estimated likelihood of finding life.
Really? How so?
Well, we've discovered that planets are far more common than previously thought.
Oh, wow.
There could be billions in our galaxy alone.
Wow.
But we also need to consider what's called the Goldilocks zone, the region around a star where conditions are just right for liquid water,
Right.
essential for life as we know it.
So it's a cosmic balancing act.
It is.
Too hot, no water, too cold, everything freezes.
Exactly. And while the Goldilocks zone is important,
Yeah.
we're discovering that life might be possible outside of it.
Really? You mean life that doesn't need liquid water?
Not necessarily. There are moons in our own solar system, like Europa and Enceladus,
Right.
with vast oceans of liquid water beneath their icy surfaces,
Wow.
heated by tidal forces. And these could potentially harbor life.
So we're not just looking for planets anymore, but moons too.
Right.
That expands the possibilities even further.
It does. There's also the possibility of wandering planets.
What?
Planets ejected from their solar systems, drifting through interstellar space.
So they're just out there by themselves.
Yeah, they might retain internal heat
Okay.
and have liquid water even without a star.
Wandering planets, it's like something out of a science fiction novel.
I know, right?
But even with all these possibilities, some scientists believe that the chances of finding another Earth are actually lower than we thought.
That's right.
We now believe that the presence of a Jupiter-sized planet in a solar system is crucial.
Really?
Yeah, Jupiter's gravity clears out debris,
Okay.
like comets and asteroids. Without it, Earth would be bombarded, making life much less likely.
So Jupiter acts as a cosmic shield protecting us from danger.
Right. It
Yeah.
seems like a lot has to go right for a planet to be habitable.
It does. There are other factors too, like a stable star and a magnetic field to shield the planet from harmful radiation.
Right.
Yeah, so maybe Earth is more unique than we realized.
Maybe so, but even if it's the only planet in our galaxy with intelligent life, there are billions of other galaxies out there.
Very true.
Right.
And we're developing more sophisticated tools to search for it all the time. So what are some of the latest advancements in the search for extraterrestrial life?
We have new space telescopes like Kepler and the Terrestrial Planet Finder.
Okay.
These instruments are incredibly sensitive
Yeah.
and can detect the slightest wobble in a star's motion, which could indicate an orbiting planet. So we're getting better at finding planets, even Earth-sized ones.
We are.
But how can we tell if a planet actually harbors life?
That's the challenge. One way is to analyze the light passing through a planet's atmosphere.
Okay.
Certain gases like oxygen and methane are strong indicators of biological activity.
So it's like sniffing out the chemical signatures of life.
Exactly. As technology improves, we'll be able to detect these biosignatures with greater accuracy.
That's exciting. But even if we find evidence of life, it might not be intelligent life, right?
Absolutely. There's a whole spectrum of possibilities.
Right.
From simple microbial life to complex ecosystems.
Yeah.
We can use our understanding of evolution on Earth to speculate about what alien life might look like.
So we're talking about more than just little green men.
Oh, absolutely. The diversity of life on Earth is incredible.
Yeah.
And it's likely that alien life would be even more bizarre and unexpected.
I can't wait to see what we discover. But for now, let's turn to a more controversial aspect of extraterrestrial life. UFOs.
Okay.
Are they real? Are they alien spacecraft?
UFOs are often shrouded in mystery and speculation.
Right.
While most sightings can be explained as natural phenomena or misidentified objects,
Yeah.
there's a small percentage of cases that remain unexplained.
So there's a chance, however slim, that some UFOs could be extraterrestrial.
It's a possibility that can't be completely ruled out. There have been intriguing cases investigated by government agencies,
Okay.
often involving multiple credible witnesses and evidence from radar or other sources.
So we shouldn't just dismiss every UFO sighting as a hoax or a weather balloon.
Right. Some cases warrant serious investigation.
Right.
But it's important to approach them with a healthy dose of skepticism and critical thinking.
of course, extraordinary claims require extraordinary evidence.
Exactly.
We've covered a lot of ground on extraterrestrial life, from the possibilities to the challenges and the unknowns.
We have.
So what's next on our journey through the physics of the impossible?
Next, we'll tackle the mind-blowing concept of faster-than-light travel.
Oh.
The holy grail of space exploration.
That's a topic I can't wait to warp into.
I think it'll be a fun one.
But first, let's give our listener a moment to process all this cosmic information.
A good idea.
We'll be back soon to explore the possibilities and paradoxes of traveling faster than light. Welcome back. Ready to break the cosmic speed limit? I mean, faster than light travel.
Right.
You know, the idea of zipping across the universe in an instant?
Yeah.
Always been a big part of science fiction.
Right.
But can it ever be reality?
Well, like with a lot of these impossible technologies, we got to start with the fundamental laws of physics.
Right.
And when it comes to speed, there's one name that comes to mind immediately.
Einstein.
Einstein, exactly.
Yeah.
His theory of relativity essentially states that nothing can travel faster than light.
Yeah.
That's a cornerstone of modern physics.
So is faster than light travel just pure fantasy? Is it completely off the table according to Einstein?
Well, it's a little more nuanced than that. Einstein's theory of relativity comes in two flavors.
Okay.
Special relativity and general relativity. Special relativity deals with objects moving at constant speeds in a straight line.
Okay.
That's where the speed limit of light comes in.
Okay.
But general relativity deals with gravity and the curvature of space-time.
Okay. I'm sensing a little wiggle room here.
Yeah.
So you're saying general relativity might offer some loopholes, some ways to potentially get around that speed limit?
Exactly. General relativity suggests that space-time itself can warp and expand faster than the speed of light.
Wait, space-time can expand faster than light? But I thought nothing could travel faster than light.
Well, it's a subtle but crucial difference. Objects can't move through space faster than light,
Okay.
but space itself can expand at any rate.
Okay.
It's kind of like dots on a balloon. As you inflate the balloon, the dots move farther apart,
Yeah.
even though they're not moving across the surface of the balloon.
Okay, that's a helpful analogy.
Yeah.
So how does this connect to faster than light travel?
Well, one concept is the Alcubierre warp drive.
A warp bubble.
It's a theoretical idea.
That sounds right out of Star Trek.
It does, doesn't it?
Yeah.
So the idea is to compress space-time in front of the spaceship and expand it behind. The spaceship itself wouldn't actually travel faster than light,
Right.
but it would ride a wave of distorted space-time.
So it's like surfing on a wave of space-time.
That's a great way to visualize it.
Yeah, okay.
There is a catch, though.
Okay, what's the catch?
The Alcubierre warp drive requires something called exotic matter.
Exotic matter.
Yeah, a hypothetical type of matter with negative mass that has never been observed.
So this warp drive hinges on something that might not even exist.
It's a major challenge, for sure.
Yeah.
But there are other theoretical possibilities for faster-than-light travel.
Like what?
Wormholes.
Wormholes.
Yeah, those cosmic shortcuts that connect distant points in space-time.
Right, like in the movie Interstellar.
Exactly.
Yeah.
General relativity allows for the possibility of space-time being warped to such an extreme that it folds in on itself, creating a shortcut.
So you could theoretically step through a wormhole and instantly travel, billions of light years.
In theory, yes.
That sounds almost too good to be true.
It does. Wormholes are also highly speculative.
Right.
We don't even know if they exist.
Yeah.
And if they do, their stability is a huge question. Not to mention the potential dangers of intense gravitational forces and radiation.
Yeah, it sounds like a pretty risky proposition.
It would be.
But even if we could find or create a wormhole,
Yeah.
are there limitations on where and when you could travel? I mean, could you really go anywhere in time and space?
That's a great question, and even theoretically, there seem to be limitations.
Okay.
It's not like a cosmic free-for-all where you can hop around the universe at will.
So faster than light travel, whether it's through warp drives or wormholes, still firmly in the realm of theoretical physics.
It is for now.
But it's exciting that there are at least some tantalizing possibilities, even if they come with, enormous challenges.
Absolutely.
Okay, ready to tackle our final impossible technology.
I'll do it.
Let's talk about time travel.
Right.
Is it really possible to journey into the past or the future?
Time travel is perhaps the ultimate mind bender.
Yeah.
Just thinking about the paradoxes is enough to make your head spin.
Exactly. If time travel is possible, why haven't we met any visitors from the future?
Right.
It's a good point.
That's the famous paradox that even Stephen Hawking used to argue against time travel.
Yeah.
But like, faster than light travel, time travel isn't explicitly forbidden by the laws of physics.
Really?
Yeah, in fact, general relativity allows for some very strange scenarios involving time.
Okay, I'm all ears.
Well, there are theoretical models of time travel that involve things like wormholes,
Okay.
spinning black holes,
Mm.
cosmic strings, all highly speculative, of course,
Right.
but based on our understanding of general relativity.
So Einstein's theory might actually allow for time travel.
In some very specific and extreme circumstances, yes.
Incredible.
But these theoretical models come with their own set of challenges and paradoxes.
Like what? Give me an example.
Yeah. Well, there's the classic grandfather paradox.
Yeah.
What if you travel back in time and accidentally kill your grandfather before your father is born?
Uh-huh.
Would you cease to exist?
Hmm.
And then there's the possibility of creating causal loops.
Causal loops.
Yeah, where an event in the future causes an event in the past, which then causes the event in the future.
That's a lot.
It's a mind-boggling concept.
Yeah, those are some serious head scratchers.
Yeah.
Is time travel something we should even be messing with, assuming it's even possible?
That's a great question. It raises both fascination and concern.
Yeah.
Some physicists believe that time travel, even if theoretically possible, might be inherently unstable and dangerous.
Hmm.
Any attempt to alter the past could have unforeseen and potentially catastrophic consequences.
Right. It definitely sounds like a proceed with extreme caution situation.
It does.
Yeah. Maybe time travel is best left to the realm of science fiction for now.
Maybe so.
It's definitely a thought-provoking concept.
Yeah.
Well, we've covered an incredible amount of ground in this deep dive into the physics of the impossible.
We have.
Exploring the science behind, some of the most fantastical technologies imaginable.
Some really mind-bending stuff.
Yeah, and I think it's important to remember that even if some of these technologies remain forever out of reach, the very act of exploring them expands our understanding of the universe.
It does.
And pushes the boundaries of human ingenuity.
Absolutely.
And I think that's something worth celebrating.
Definitely.
So a huge thank you to you for joining us on this incredible exploration.
My pleasure.
We hope you've enjoyed our deep dive into the physics of the impossible.
It's been fun.
And remember, keep looking up at the stars and dreaming big.
Absolutely.
The universe is full of wonders.
It is.
And who knows what amazing discoveries await us in the future.
I can't wait to find out.
Until next time, keep those minds open and curious.
And never stop exploring the impossible.